Welcome, everyone, and thank you for joining our discussion today. This is Mike Furstenberg, and I will serve as your moderator for this webinar. In keeping with standard practice, all participant lines are muted. Please enter any questions you may have in the question box at any time. We will address all submitted questions at the end of the presentation. All webinar registrants will receive a follow-up email including information on how to access a recorded version of this webinar and registration information for upcoming webinars on additional topics. Today's topic is, what do really secure OT or ICS sites do differently? Presented by Andrew Ginter. Andrew is the VP of Industrial Security at Waterfall Security Solutions and works with many of the most secure industrial sites on the planet. He is the co-chair of ISA's SP99 Working Group 1. He's a co-author of the Industrial Internet Consortium Security Framework and the author of 2 books on industrial security: SCADA Security, What's Broken and How to Fix It, and Secure Operations Technology. Andrew spent 20 years developing SCADA systems and IT/OT middleware products, and another 20 designing control system security products. He holds a BS in Applied Mathematics and an MS in Computer Science, both from the University of Calgary. Andrew?
Hello, Mike, and thank you for that. And, hello, everyone, and thank you for joining us. Thank you for listening in. As Mike said, today we're going to be talking about secure operations technology. This is my latest book. It is about what the world's most secure sites actually do. I mean, I work for Waterfall. The book is not about Waterfall. It's about what we see our customers doing. At Waterfall, we serve the most secure sites on the planet. What we see them doing is they ask different questions, they get different answers, they see the world differently. So this presentation and the book are about what those sites do differently. Waterfall does still have an inventory of these books. We are giving them away free. There will be a URL on the end of the presentation that you can click on and request a free copy. So let's get started. When we talk about what industrial sites do differently, let me say just a word about do differently from what. This is conventional cybersecurity here. This is, basically what was documented in pretty much all cybersecurity standards and advice before about 2012, 2013. What is standard conventional OT industrial cybersecurity? It's intrusion detection, security monitoring, incident response, recovery, practiced recovery capabilities. It's long passwords and permissions, role-based permissions. It's antivirus and security updates and host hardening and firewalls and encryption. All of this stuff. And in the recent days with the ransomware coming, it's backups. It's testing those backups so that if we do get hit, we can recover. All of this, it's a lot of stuff. All of this is because there's a lot of different ways for the bad guys to get into our networks. We have contractors carrying laptops into our networks. We have employees carrying USB drives full of who knows what into our networks. We have connections through firewalls from external networks into our networks, sending who knows what into our networks. And so, we have a lot of stuff to worry about. There's a lot of solution here. Part of the problem is that some of these solutions really are quite expensive. Security updates in particular are, as anyone who's practiced industrial cybersecurity knows these are very costly systems, costly programs because of the amount of testing we have to do before we can trust new software on these sometimes safety critical, always reliability critical networks. It's not easy being the good guys. And when we're done all that, what are we left with? Well, we're left with residual risk. There's only 3 things we can do with risk. We can mitigate risk, which means do something about the risk. Reduce the the possibility of attack, reduce the frequency of attack, or reduce consequences so that if we do get attacked, less bad things happen. We can transfer risk, which is pay somebody, usually an insurance company, pay them to accept the risk for us. So that if the risk is realized, they cover the cost of the consequences. We don't have to do it ourselves. And if we cannot mitigate risk or transfer risk, we have to accept the risk, which means we do nothing about it. And if the risk is realized, well, we suffer the consequences. There is always residual risk. No security program is perfect. And, the question is, what do we do about this risk? A lot of people look at residual risk and say, well, we have to accept it. Because we accept the risk, it must be acceptable. Here's the first difference. What we see at SecOT sites is they look at the residual risk from these conventional cybersecurity programs. They do not accept the residual risk. They raise the bar and they do extra to mitigate more of that residual risk. So, brings us to SecOT. What is SecOT? What do people do differently? Well, the first thing that we see people doing differently in the SecOT world is priorities. What is the number one priority on all enterprise networks for cybersecurity? It is protecting the information, protecting the confidentiality, integrity, availability, the CIA of the information. Sometimes, on industrial networks, people say, no, we're protecting the information, but we're protecting the AIC, availability is first, or integrity is first. What we see at truly secure industrial sites, they do not try to protect the information. Their job is to protect safe, continuous, correct, and efficient physical operations. Protect physical operations from information. More specifically, protect physical operations from attacks that may be embedded in information. So that's a different focus. That's a different question. Once you start asking the question, how do I get protected from information? You start getting different answers. So this is what I'm going to explore. And don't get me wrong, SecOT sites generally do everything I'm saying in addition to all of the conventional stuff. The SecOT sites do all of that security. I'm not saying any of that security is wrong. All of the conventional security is needed and is done at SecOT sites. Now, these sites might relax just a little bit more about the most expensive and the least effective security, the parts of a security program, like security updates. They might relax just a little bit. They might reduce the frequency of those updates. They might take just a little longer doing their testing, doing a more thorough job. But they can only do that because they have implemented these other very strong measures that I'm going to be talking about. They do all the conventional stuff. It's just not enough. So they do extra. Where do they start with the extra? Well, this is, this was the topic of my first book in terms of the perspective. So the next level down on the perspective saying, we have to do more. We're trying to protect from information. This perspective, I tried to capture as the first three laws of SCADA security. So let me start with law number 3 and work my way back. All cyber attacks are information. Every bit of information can be an attack. A single bit can be an attack. A bit that's on saying turn on the pump could be exactly the right thing to do now and exactly the wrong thing to do 10 seconds from now. It's supposed to be 0, that bit, 10 seconds from now. So, so this is the information flows are very important. In particular, information flows through our perimeters, and I'm going to be talking about that in another couple of slides. Let's look at number 2. All software can be hacked. All software has bugs. I wrote software for 30 years. In spite of my best efforts and the best efforts of all my colleagues and all the teams I've ever been part of, every piece of software we ever produced had bugs. And some of those bugs were security holes. So in practice, all software can be hacked. Some of those security holes are known to the developers and they're busy trying to fix them. Some of them have fixes already. Some are unknown. These are the 0 days. And what we do is if we go back and look at all of the measures in that conventional security slide, there's only two kinds of security measures there. There's people and there's software. People are imperfect. Software is imperfect. This is part of the perspective of the most secure sites. They want something more than software. And number one, nothing is secure. Security is not a binary yes or no thing. The question, are we secure, is meaningless. It's like the question, are we safe? Well, yes. Could we be safer? Yes. Security is a continuum. You can always be more secure or less secure. The question, are we secure, is meaningless. The question, how secure are we, has an answer. The question, how secure do we need to be, is even more important. This is the question we see SecOT sites asking. They're asking, how secure do we need to be? They decide how secure they need to be. They find that their existing measures are inadequate, and they do more. What do they do more? So I talked about the perimeter. I talked about information flows. So let's look at that. Law number 3, all cyber attacks are information. Fundamentally, the only way a control system can change from an uncompromised state into a compromised state is if attack information moves into the industrial system through a physical or a network perimeter. All attacks are information. There's no other way to compromise an industrial site. The attack information has to come through a perimeter. So looking at our perimeters is very important. The IT gurus will tell us the perimeter is dead. Where is the perimeter around our cell phones? How much important business data is on the cell phones? And they're right. The perimeter is dead on IT networks, on enterprise networks. But think about every industrial site that any of us have ever been to. Every power plant, every I don't know, pipeline, every refinery, every water treatment plant. There is always a fence around important industrial sites. You might ask, who decides if a site's important enough to put a fence around? Well, the physical security people decide that. They've been doing this for centuries. Every important site has a fence around it. And every place that there is a fence, a physical perimeter, guards, gates, and guns, there should be a cyber perimeter as well. Secure sites, the methodology for securing, one of the things secure sites do extra to conventional security is they define their perimeters, and then they take an inventory of all of the ways that information can enter the industrial network through the perimeter. It might be USB keys. It might be new computers being shipped from a supplier. It might be, a firewall with messages coming in. Inventory absolutely all of the ways that information can enter the site. That inventory of incoming information flows is also a complete inventory of attack vectors. And now they set out to systematically control all of those attack vectors. And ideally, they control those flows of information physically, not just with software. Yes, they use software, but they also add a layer of physical control over information flows because rule number 2, all software can be hacked. So how do they do that? Well, there's only 2 ways that information can move. There's only 2, online and offline. Online is information that's transmitted. Nothing moves physically, but radio waves and light through a fiber or electrons in a wire. Nothing seems to physically move, but information moves. That's online. Offline is everything else. Offline is where information is physically carried from one place to another. So chapter 4 of the book is all about protection from offline information attack flows, or if you like, attack information flows. None of these are particularly surprising to anyone who's familiar with the conventional approach to cybersecurity. We all know we have to control removable media. Wherever practical, we glue shut all of the ports the USB ports, the CD drives, even the floppy drives on some of these older systems, glue them shut, physically remove them so that they cannot be used anymore. It's not physically possible to move information through those ports. Use an antivirus scanning kiosk or workstation at every physical site. Just don't let USB devices into the system anymore. Stick them in the workstation, scan them with 8 or 10 different antivirus engines, take the files that need to move into the industrial network, copy them to brand new media, a CD or a write-once CD or a fresh USB drive. No media comes in to the site through the physical perimeter. Scan the drive, pop the new media straight into another computer, a computer on the industrial network sitting at the perimeter checkpoint, load the files over onto that computer, and now that computer can send those files through the industrial network wherever they're needed in the industrial site. And if we have to use USBs on the industrial network, well, they're copied to known clean drives. We're not taking, who knows what from the internet coming in. No external device, much less laptop, comes in and touches the industrial network. And that's for the simplest of files whose content we are very confident of. If we have complex files, let's say new antivirus signatures, security updates, who knows what's in the security update, these files do not go directly into the industrial network. They go onto a test bed. The test bed is, most sites already have a test bed. It's heavily instrumented for threats, to make sure that the new software, the new information artifacts are going to operate correctly, safely, reliably, continuously. What we see SecOT sites doing is taking their test bed and instrumenting it heavily for security. The test bed becomes a sandbox. Put the new artifact on the test bed, advance all the clocks, check if our hard drives just got erased. Whoops, whatever that was, it was ransomware. Good thing we didn't put it on our industrial network. Turn on all of the auditing, all the logging, investigate the false positives, gain confidence, not just in the safe operation, the reliable operation, but also the secure operation of new information artifacts. So none of this is new to people familiar with conventional security. What's different is the intensity that we see the world's most secure sites bring to this process of, eliminating as much as possible incoming information and testing and controlling, disciplining the flow, the inbound flow of information to deal with attacks that may be embedded in the information. So, for a concrete example of that, let's say we had to leave USB ports enabled on a couple of machines because that's how the machines work. You can't disable the ports. Let's say we've put some software in place to monitor who's sticking stuff into them and what they're doing. And every time there's an unauthorized USB connected to this port, we get an alert saying, hey, I just blocked Andrew from mounting the USB drive. Well, in the industrial world, most of us are familiar with OSHA, the Occupational Safe and Healthy Administration, Health Administration, who governs safe operations. The OSHA Nearmiss safety protocol is a process where if there's an incident, a safety incident, let's say, there's 10 tons of material being lifted by a crane, and Andrew, with his hard hat on, walks under the 10 tons, and 10 seconds later, after Andrew's clear, the chain breaks and the 10 tons drop to the ground. Well, Andrew wasn't crushed. That's me. That's a good thing. But it's a near miss. If circumstances had been just a little different, we'd have had a safety incident. You write these things up. And so what we're seeing the world's most secure sites starting to do, this is brand new, is cyber near miss programs. Every alert that says, hey, I just blocked Andrew from sticking a USB drive in is logged as a cyber near miss. Just like safety reports, these reports are aggregated, they're analyzed, typically monthly, and they're followed up. If Andrew needs remedial training on USB drives, let's give it to him because he was 32% of last month's cyber near misses. What we hear from SecOT sites is that the combination of their offline protections and these near miss programs pretty much eliminate errors and omissions with USB drives, laptops, and other devices. Now, whereas the offline stuff was reasonably familiar. The intensity is different, but the concepts are familiar. The online controls that we see SecOT sites deploy really are very different. The big news at the world's most secure sites, they forbid firewalls between control-critical industrial networks and any external non-critical networks, networks that are not managed according to the SecOT discipline. SecOT sites permit only unidirectional gateway technology at those connections. They still use firewalls extensively inside the networks, the critical networks. They still use them outside, but they're not permitted at the boundaries. Most SecOT sites deploy, they put in place one layer of unidirectional gateways. They've got multiple layers of firewalls in a defense in depth, Purdue-style stack of networks. They pick one of those layers and replace them with unidirectional protection. So for anyone not familiar with the gateways, let me give you a quick introduction. Here's a look inside. Everything in the red box at the center here is the unidirectional gateway. It's typically a 1U rack mount unit, but I've called it out here so we can see all the pieces. Inside the unit, there are 2 conventional computers and some special hardware. The hardware is physically able to send information in only one direction, from the industrial network to the enterprise network. Nothing at all gets back in. It's not physically possible. I mean, there's a fiber optic transmitter on this circuit board, a receiver on this circuit board, a short, 18-inch typically piece of fiber connecting the two. There is no laser on the receiving circuit board. It's not physically possible to send any information back in. So we can send information out. We can monitor what's going on in industrial operations, but nothing gets back in. Remember, third law of SCADA security, all cyber attacks are information. If no information gets back, no attacks get back. It does not matter if an attacker has fuzzed zero-day vulnerabilities in every piece of software on the planet. It does not matter if they've stolen every password for every computer on the planet. It's not physically possible to send attack information back into the protected industrial network. So the hardware is one way. The software, there's always software in a unidirectional gateway. The software replicates servers and emulates devices. So for example, if there's a historian on the industrial network, the software logs into the historian, username and password, nothing tricky, asks the historian for all the data, pushes the data through the weird one-way hardware, and on the other side, the software logs into an identical historian. If it's SQL on the inside, it's SQL on the outside. Pi on the inside, Pi on the outside, inserts the data into the outside database, and now there's a copy of the database on the enterprise network. Users and applications on the enterprise network who want that data, they connect to the database normally, and off they go. They have access to the data normally, bidirectionally, logging in their usernames and passwords. So physically one way out, and logically replicating databases. Now, you might ask, it sounds good, but how is this practical? A lot of people find this very confusing. A lot of industrial sites have a lot of industrial networks that all cooperate very closely with each other. It's not one network. The operator HMI network needs information from the communications front-end network. The historian DMZ needs information from the PLC network and from the SCADA network. They are all talking to each other. If everyone is unidirectionally sending and not listening, how can this work? And you're right. That's not how it works. What we see these industrial sites doing is, yes, they have lots of industrial networks. They take most or all of their industrial networks and wrap them up and call them one control critical network. So they think of all the, this whole set of 1, 2, 3, 4, 5 industrial networks as one control critical network. They demand unidirectional communications at the critical boundary between anything in the control critical network and anything outside. It's only one boundary, not all of them. They do, as I said, permit firewalls. They use firewalls routinely inside the control critical set to communicate between all of the sub-networks in there. They use it, of course, out on the IT network. It's the boundary between the control critical network and the external network that they deploy the gateway on. Now, you might still say, you know, I don't know if that's going to work. I mean, people have been getting more connected for, 30 years. Well, let's have a look at the industrial Internet of Things. Okay, the trend for 30 years is more and more communications, more and more connectedness. The industrial Internet is held up as the future of industrial security. But let's look at how it really works. I mean, I'm a co-author of the IIC's security framework document. The document is based on the IIC reference architecture. This architecture was developed and was agreed to by the consortium of over 300 vendors. This is their diagram. Okay, I cut and pasted it. It's even their colors. The industrial control networks are at the bottom. Information flows are the arrows. Inside the control network at the bottom, information circulates really quite freely. Think firewalls inside of the control critical networks. But at higher levels, there are white, green, and red arrows. My apologies to the red-green colorblind in the audience. This is the IIC's colors. The white and green arrows are safe communications. These are the arrows from lower levels to higher levels. That's safe. You can't compromise lower level systems by sending information to higher level systems. The white arrows are arrows between the same level in the architecture. The downward arrows are all red. All the downward arrows are some kind of control. They're called out in the reference architecture as control. Every message sent to a lower level architecture causes computers in that layer down to execute instructions they would not otherwise have executed. Every single message is a kind of control. It's a potential attack. And of course, the most dangerous control messages are the ones entering the control critical network at the bottom from higher layers in non-critical networks. What do we do about these messages? Well, if all we have is a firewall between layers, well, what can we do? We open another port. To a man with a hammer, all the world's a nail. To a man with a firewall, all problems are solved by whack, opening another port. What modern practice demands, what's documented in the ISC security framework, is disciplined control. When we need to send control information into a more critical network, and often we do need to, when we need to send stuff in, we need to use the most secure, the safest way to communicate that very dangerous piece of information, the safest way that meets the business need. And if I may, all the offline mechanisms I mentioned in chapter 4, a slide earlier, they're dealing with kinds of control as well. The OT testbed is a very important kind of way to discipline the flow of control information, new information, into the industrial network. It's offline, it's very slow, but it's as safe as we know how to make it. So we're talking about online information flows. How can we discipline them? Here's a classic design. A control network has a lot of equipment in it, including an OPC server. There's a historian in the DMZ between the control network and the IT network, and there's business systems, clients in the IT network that need data from the historian to do billing, to optimize operations. The business network sends queries, questions into the historian and gets data back. The historian sends OPC queries into the OPC server and gets data back. So how could we draw a control critical boundary? There's information flows all over the place here. There's queries being sent in one direction, there's stuff coming back. If we send polite queries, we get data back. If we send impolite queries, we're attacking systems we're communicating with right through any firewalls that might have been placed in between these networks. Well, here's one thing we can do. We can deploy at the boundary between the control network and the DMZ. That's one possible design. There's several possible designs here. The Unidirectional Gateway technology, again, combination of hardware and software. The software polls the OPC server and grabs snapshots of the state of the server. We typically send a request, once a second, but it's configurable. Once a second saying, give me all your tags and values. The gateway pushes those tags and values through the weird one-way hardware, and on the outside, the gateway software is a standard OPC server. It has all the latest tags, all the latest values. It emulates the real OPC server. The historian sends its OPC requests to the gateway OPC server. And we get answers back to the historian from the gateway server because it is a standard compliant OPC server. We never opened a port. We never let the queries through. We eliminated the need to send any requests at all from the DMZ into the industrial network. The best kind of information, attack information discipline is getting rid of it entirely. What does this mean in terms of the SecOT sort of theory, the very high level theory? What we've done is we drew our control critical network boundary around the control system containing the OPC server. Everything else is non-critical. We deployed the Unidirectional Gateway technology in only one connection. All these other connections are unchanged. It's the connection between the control critical set of networks and the non-critical set of networks. There are some, 20 networks, unidirectional network designs documented in Chapter 6. I'm guessing a lot of us have heard of this unidirectional stuff before. I'm thinking, we might not really have looked into it. We might have looked into it a little and, concluded that it can't possibly work for us. Chapter 6 is new. 20 architectures documenting how lots of different kinds of sites with different kinds of networks and different communications needs, how they use unidirectional gateway technology. The OPC example we just went through, that's pattern number 2, device emulation. The gateway emulates the OPC server to the DMZ network. In a couple of years, this is the part of the book that's going to need an update the most, because we keep seeing SecOT sites inventing new kinds of unidirectional architectures. And the reason it was important to document these things in a book is because a bunch of these designs are really kind of counterintuitive. So let me give you another example. A lot of people might say, hey, yeah, you really cheated on that OPC example. You managed to eliminate inbound communications entirely. That's certainly discipline, but it's not really control, is it? Here's an example of a network architecture where we need inbound communication. Many industrial sites need to push antivirus systems into the industrial system on a regular basis. Batch sites like mines and refineries, batch systems need to top up their inventory of production orders a couple of times a day. A production order is typically a small XML document. These small documents, the antivirus signatures, the production orders, they're important to the site. How do we deal with this? Well, what we see people doing is deploying a reversible unidirectional gateway. The gateway replicates OPC servers and Pi servers out to the enterprise network all day long, but a couple of times a day it reverses orientation. Now, a reversible gateway, Waterfall has one of these. We call it a flip. The reversible gateway is a unidirectional gateway. It can only send information in one direction. It only has one transmit circuit board and one receive board. It can only go one way. But there's a button on the front of the device. If you press the button, it is as if the device picks up, flips over, and sets down. It can be one way out or one way in, but never both. There's only one transmit circuit board. And the software cannot control the flip, the reversal. That's done in the hardware, but the software can detect the reversal and can say, oh, look, it's 2 in the afternoon. The device is just reversed. It's time to pull my antivirus signatures and top up the production orders. And so it goes out and fetches antivirus signatures, checks the authenticity with the crypto stuff, sends it through, checks it again on the inside, and hands those signatures to the right systems in the plant, typically to an antivirus server. We generally don't push these signatures straight into plant systems. Same thing for the production orders. So, the gateway replicates servers and emulates devices both ways. The gateway never forwards network traffic like the firewall does. Network traffic containing who knows what attacks. It pulls the signatures from a known place. It checks their authenticity. It pulls the batch orders from a known place. There's discipline for you. We don't just open another TCP port and forward whatever packets you like, whatever packets match the rule. We pull exactly the information we need. We check its authenticity. We send the information through to exactly where we know it's going. There's no network packets passing through here. It's the high-level information, the application-level information that's coming through. And again, in terms of the SecOT model, everything on the left, the entire industrial network is modeled as a control critical network with the unidirectional technology at the boundary. That's all. So one element of IT security, of sort of conventional security that is becoming increasingly important in industrial systems is security monitoring. I mean, rule number one, SCADA security law number one, nothing is secure. And so we need to monitor stuff. We need to understand what it's doing. If we start seeing out of ordinary behavior, we need to investigate that. How do we do that? Nowadays, I mean, this wasn't true 10 years ago, but nowadays there's a whole host of OT intrusion detection sensors from a host of vendors. So this is a really hot space right now. How do they work? Well, they connect on one side to a mirror port on a bunch of industrial switches, and on the other side, they've got a management interface that sends alerts to a SOC. SOC might be in another city, it might be in the cloud, it might be outsourced. The question is, where do we put the management port? If we connect it to the industrial network, we get resistance from operations because these sensors need to be managed. They need to be tweaked. They need to be adjusted on a regular basis. You typically adjust the sensor to be a little bit too sensitive. It produces, some extra, false positive alerts, false alarms. You don't want to be insensitive. You want to adjust it just on the edge of producing the occasional false alarm, which means we've got to log in and adjust these things, saying, that false alarm you've been doing, stop sending that, but keep sending everything else. So if we have the 37 security analysts in our SOC logging into every one of our industrial networks a couple of times a week to reach these sensors, operations is going to say, how many people do you want me to give VPN connections into all of our industrial networks? Who are these people? What are they doing? What are they doing it to in our networks? These networks are fussy. You cannot have, untrained people coming in here and doing who knows what. You get resistance. But if you put the management interface on the IT network, on the enterprise network, you got this same problem. Now you've got the opportunity to steal some passwords, log into these devices, these sensors, and send messages back into the industrial network, attacking them, pivoting the attack through the sensor. A lot of people say, but mirror ports are unidirectional, aren't they? Well, they aren't. Switch vendors often say they're unidirectional, but the documentation is inaccurate. I've seen switch vendor documentation contradict itself about unidirectionality in 2 adjacent paragraphs. And even if the port is unidirectional in some sense, it's software. Steal the password to the switch, reconfigure it, and now the port's bidirectional, and there's no hint that this has happened. Attacks can pivot. So what we see in a lot of SecOT sites is, yes, they are bringing recently they're bringing the operations networks into the security monitoring program, and what they're doing is connecting the mirror ports to a unidirectional gateway into the intrusion detection sensor, and they're putting the sensor on the enterprise network. Why? So that security analysts from the SOC or even from an outsourced SOC can log into these sensors routinely without affecting operations at all. The gateway emulates the industrial mirror ports to the sensors. The operations department, just doesn't want any kind of new connectivity coming into their network. No matter how useful it's supposed to be there, every new connectivity is a threat. Here's a solution that lets us see the industrial network, and it's not physically possible for us to affect the network in any way. So that was sort of the very whirlwind tour of SecOT that I had for you. If I could say a few words about Waterfall, we are the OT security company. We produce a whole line, a whole family of unidirectional technology and connectors. We were founded, 13 years ago. We got a lot of sites all over the world. We're headquartered in Israel. We're deployed in lots of different industries, pretty much all of the critical infrastructure industries. We got example sites all over the world. Sales operations on 3 continents. So this is what we do. We're a technology provider, and our focus is the unidirectional stuff. If you're interested in industrial security, so I'm backing up even more. Let's leave SecOT aside for just a moment. I did want to put a plug in here for the Industrial Security Podcast. This is a podcast that is not, Waterfall sponsors it, but it's not about Waterfall. Every podcast episode has a different guest. The guests might be vendors, the guests might be government agencies, they might be owners and operators, each of them talking about different things, talking about their perspective on industrial security. I've been talking about the high-end perspective on industrial security. There's a lot of other perspectives of this elephant. So if you're interested, the podcast is free. Go to your favorite podcast app and enter industrial security and you'll find it. Or you can come to the Waterfall website. And we have, not just the nuts and bolts technical stuff that I'm talking about. We have, we've had people on who are on, boards of directors of power companies talking about governance for cybersecurity. We've had recruiters on talking about, recruiting talent in this space. So if you're interested, tune in. And let me wrap up here. So back to the question of what do the world's most secure sites do? The threat environment is getting steadily worse. Okay, the bad guys are getting more and more powerful attack tools, more and more powerful attack capabilities. Ransomware, the bad guys are finding ways to monetize, to profit from attacking us, which means they're only going to do more of it. What all of us do in response to this, everyone who is involved with an industrial site, all of us respond to this worsening threat environment by increasing the strength of our security programs. So if we do, look at a chart and say, well, let's do a survey of all the world's industrial control systems. How secure are they? There's 10% that are not very secure. There's, 50% that are this secure. There's, everybody is at least, is less than this secure. The SecOT sites are on the very high end. What we see, because of the worsening threat environment, the entire bell curve of security posture strength is shifting to the right. We're all making our defenses stronger. We have to. So what I'm suggesting is that the techniques I've been talking about here, the offline information flow controls, the online information flow controls, attack information controls, these techniques, like it or not, lie in all of our futures. The entire curve is shifting in the direction of what the world's most secure sites are doing today. What are they doing? In a nutshell, they've raised the bar. They have raised the bar to the point where the only way to compromise the industrial site is physically. You've got to put your own liberty at risk by physically breaking into the site or persuading someone else to break into the site to compromise the site. That's the only way you can do it. These sites, that's how high they set the bar. That's their goal. Zero, there should be zero chance that anyone sipping coffee in a city on the other side of the planet poses a cyber risk to the industrial site. They want physical, these sites want physical control over their information flows. So what they do is they inventory the information flows and they physically control them with offline controls and with unidirectional controls. If you'd like to know more about the methodology of the world's most secure sites, as I said, Waterfall still has an inventory of my latest book. Go to the URL on the bottom of the screen. You can request a copy. We can ship to most of the places in the world. We've lately had trouble shipping to India. We just can't seem to get through customs, but we will do our very best to get you a copy. you've got my email there. I'm always keen to get feedback. If you found this webinar useful, if you found the book useful, if you didn't find it useful, send me a note. Feedback is extremely valuable, good, bad, or ugly. If you've got suggestions for topics you'd like to hear in future webinars, I'm currently working on a risk management book. You'll see some webinars on that, as I get the material a little bit more finished. Send me ideas. We would love to hear from you. That's what I had for you. Thank you so much for listening. Mike, do we have questions?
Well, thank you, Andrew. And yes, we have questions. And thank you to everybody online who has been submitting questions. We've got quite a few. If you haven't gotten your question submitted yet, please do get it in. We will do our best to address all of the questions that we can get to within the time frame this afternoon or this morning or evening, depending on your geography. So with that said, Andrew, our first question comes in. Do you see many requirements for symmetrical unidirectional gateways to support both directions of data flow? In such cases, how do you maintain the security requirements?
That's a good question. So let me answer the first part first, which is we do not see that very frequently. We do see asymmetrical connectivity requirements. So I gave the example of OPC being a flip, the Waterfall flip, a reversible gateway, replicating OPC out 23 hours a day, and replicating antivirus and production orders in briefly a couple of times a day. But that's an asymmetric connection. There's different stuff coming out versus going in, different systems being replicated. There's often 4 CPUs involved, completely different CPUs involved in the one direction of data transfer versus the other direction of data transfer. The question of symmetric communications we see much less commonly, but we do see it in rare cases. So if you look in the 20 designs, I do have one of those examples. The one that springs to mind is balancing authorities in the power grid. They need to send information to other authorities, other utilities, saying, give me more power, give me less power. They need to read values from those same utilities and even other utilities, saying, how much power are you using right now? How much are you producing? How much are you using? They got to balance all of this in real time, second by second. And they do it over the ICCP protocol. So what we see in that case is 2 unidirectional gateways. One oriented outwards, replicating the energy management system from the balancing authority out to the network so that the other utilities can poll the ICCP replica and see what the balancing authority is telling them to do. And a second gateway that polls all of the, typically 24-ish power utilities, polls their ICCP servers and gathers all of their values and all their tags, pushes that through the weird one-way hardware, and on the inside, emulates those 20-odd ICCP servers so that the energy management system at the balancing authority can poll those 20-odd replicas. So yes, we see it occasionally. What we do is replicate systems in both directions. They happen to be the same kind of systems, but they're different systems that we're replicating. What we never do is what a firewall does. A firewall sends a message through one unidirectional line, a twisted pair in a cable, sends a message to another network. The answer comes back over a different cable. You can think of a twisted pair cable as one way out and one way in, because there's one twisted pair is one direction, one is the other direction. How secure is that? It's not. Firewalls forward network traffic. The gateways never forward network traffic. When we have that kind of symmetric connection, it is possible. And what we do is replicate servers in each direction. We never send a query out one gateway and the answer back the other. That's what firewalls do. It's not secure enough. So I hope that answers the question. There's more information on this in the book.
So before we continue with the technical questions, we have a few people asking about a logistical question, which is there a digital version of the Secure Operations Technology book? Because they're unsure of the ability of the post to get through given the current pandemic or other similar situations. So yes, there is a digital version. It is available on Amazon. So Andrew, are there other digital platforms where this book is available?
No, unfortunately, the book is currently only available. If you want digital form, it's only available on the Amazon Kindle platform, and it's about $7.50 US. I haven't figured out a way to give away Amazon Kindle stuff, so that is what it is.
We'll go back.
So, yeah, go for it.
We'll go back to the technical questions. We'll do our best to get a copy of the book into everybody's hands through whatever means we can achieve, given the pandemic situation. And speaking of the pandemic situation, we have a couple of questions coming in, specifically related to travel restrictions given the global situation right now. How are these secure operations facilities handling remote access?
That's a good question. So let me give you sort of two layers of answer. For the duration of the pandemic, or at least as far as we can see, through the end of September, Waterfall Security Solutions is making licenses for remote screen view technology available free of charge. You do need the hardware, so this is something that's of interest primarily to our existing customers, where they want to install a new license on an existing unidirectional gateway. What it does is enables the remote screen view functionality. Remote screen view makes conventional connectors replicate servers or emulate devices. Remote screen view is a connector that replicates screens. So classic example is let's say we have a remote, let's say the turbine vendor is, we've replicated the turbine control system out to the enterprise network, where the vendor can VPN and monitor the turbine continuously. Every couple of months, though, they find in their monitoring a vibration problem that's building up, or a hotspot on a gas turbine that's building up, and they need to adjust the turbine in order to fix the problem. So what they do is they call up the site, they say, can I have an hour on Thursday, let's say 3 o'clock, we need to do some work on your turbine. Yep, 3 o'clock comes, the site calls the vendor, they know who they're calling, they get a voice on the phone, yep, you're the vendor, here we go. And the site turns on remote screen view. And the vendor logs into a web server and can see the screen, much like remote desktop. But it's the screen images that are being sent through the hardware. Nothing gets back into the industrial network. The vendor can bang on their keyboard all they like. Nothing gets back. It's not physically possible. But the vendor can give instruction. The people at the site can move the mouse. It usually is an engineer at the site moving the mouse. The vendor can, say, look, bring up the vibration diagnostics. And they can say, no, that's communication diagnostics. 2 further down. There you go. That's vibration diagnostics. Can give real-time advice. The vendor sees the process as supervising the site for a complex fix. The site sees the problem. I mean, whose turbine is this? It's the site's, thank you. They see the process as supervising the vendor. Both sets of needs are met. That's one example of that's the most secure remote access technology on the planet. There are other options that are documented in the Black Book, not as secure as remote screen view, but all much more secure than a firewall. So yes, people might imagine that unidirectional technology rules out remote support. It does not. If we have third parties calling in who are unknown to us, we haven't done background checks on them, like the vendors, we use remote screen view. If we have insiders, trusted insiders coming in, we use a different technology. So there are definitely remote operation options. This is vital in today's world.
Very nice, very nice. So we've got a handful of questions that relate to how the Unidirectional Gateway functions. I'm going to attempt to cobble them together into one question. And it seems that the most common bond in these questions is this protocol, OPC, whatever it may be, it's based on TCP/IP, and TCP/IP requires a three-way handshake. So how is this working? How does the ACK get delivered back to the sender?
That's a good question. And again, it's the ACKs getting delivered back to the sender. That's something firewalls do. So let's look back at the diagram here. What we have, maybe I should hang on. Let me see if I've got. Maybe this diagram's a little better. Let's go with this one. Okay, so we got, inside the gateway is a CPU on the left, a CPU on the right, and the weird one-way hardware in the center. The CPU on the left opens a TCP connection to the OPC server over a regular switched network. Three-way handshake happens between this host and this host. Can you see my pointer here, Mike?
Yes, we can see it.
Okay, happens between these two hosts on the network. It's a standard back and forth. The queries go to this host, the answers come back. We build up a snapshot of tags and values. Think of it as a comma separated value file. It's not, but think of it. We build up tags and values. Okay, we send those tags and values, the CSV, across the weird one-way hardware. On the other side, we are a standard OPC server. The historian connects to us with a three-way handshake over normal networking, sends us queries, we send responses. We have all the tags and values in our heads. We can send the very latest values to the historian. We have never forwarded any messages from the industrial network to the DMZ. The pull request here is something we create. The response, this response is, here's all my tags and values. This query might be, give me 3 tags. This response is, here's your 3 tags. These packets are entirely different. The OPC conversation between the gateway and the OPC server ends. It's over. It's finished in this host on the left side of the gateway. The gateway throws away all of the OPC response packets after it pulls the tags and values out of them. The OPC conversation over here is entirely new. It's entirely different. It's different questions for different tags. It might be at a different frequency. None of these packets make any sense out here. We never forward messages. The TCP conversations end in this host. This, TCP conversations on the DMZ side end in the host on the right side of the gateway. I hope that answers the question.
Great. So we do have a question in the form of an objection, and that is, everything we buy today needs connectivity, whether it's sensors, industrial sensors for the plant, or home technology like thermostats and smart light bulbs. So this objection is that restricting information flows seems to be backwards looking.
Well, again, I would remind the person asking the question about the Industrial Internet Consortium. This is 300 vendors who agreed on the right way to design industrial Internet of Things stuff. And they distinguish monitoring. Here we go. Is monitoring. Monitoring is mostly harmless. The consequences of tampering with the data once it reaches the business network are business consequences, consequences that enterprise IT teams know how to manage. They manage them routinely. The consequences of sending control information back into the industrial network can be truly nasty. On the IT world, if you compromise a bunch of machines, what do? The incident response team shows up, they identify the affected machines, they isolate them, they erase them, they restore them back up, and they repeat. This is the problem. When we control industrial processes, be they, stove tops in your home where you might light things on fire, or turbines or catalytic crackers in industrial sites, when we control them, the consequences cannot really be restored from backups. We cannot restore human lives or burnt down houses from backups. So the question is, when we look at these connections, what we want to do is we want to give consumers of the data, and the consumers are primarily on the outside networks. We want to give them access to the data. We do not want to give them access to the systems. This is the problem with firewalls. If you send the query into the system, you're accessing the system. We, the unidirectional world, sends the query to the replica. The query never gets to the system. There's access to the data, but not the system. If you need to control the system, you've got to ask some really hard questions. And it is possible to control systems unidirectionally, but you think really hard about it. How many machines on the internet should be able to control our power plants and our railway switches while the trains are running? How many machines on the internet should be able to control those physical processes? How many machines on our enterprise networks should be controlling the operation of 2 gigawatt power plants and massive boilers and railway switches? How many? Just about none. Often it's none. You don't control railway switches from the internet. Are you crazy? You do it from a much more trusted network. So the lesson is, the trend for 30 years has been greater connectivity, yes, and this is biting us right now. This is a problem. The trend looking forward, the way we're going to get safe control, safe operations, physical operations, is by sharing the data, by moving the data, not giving the consumers who need them access to the data, not connecting the systems the way we do now, indiscriminately. So I very much believe in the future of automation, the future of data moving all over the place, but we have to be very careful about connecting systems and the consequences of connecting systems. Even though that's the easiest thing to do, it is often the very wrongest thing to do for systems whose compromise has unacceptable physical consequences.
Oh, thank you. We've gone a couple minutes past the top of the hour, so I do want to be respectful of everyone's time, and I want to say thank you to Andrew. That was a perfect spot to conclude our webinar here today. As a reminder, all webinar registrants will receive a follow-up email, which will include information on how to access recorded version of this webinar, along with registration information for some upcoming webinars on other topics. With that said, I want to thank all of our attendees who have listened intently and submitted some fantastic questions. I apologize that we did not get to all of the questions. We will do our best to answer them offline. And at this point, I'd like to give Andrew the opportunity for the last word.
I just want to echo your thanks. Thank you, Mike, for organizing this, and thank you, everyone, for attending. And as I said, my email is here. Feel free to reach out directly to me. I would, I'd love to hear your questions and answer your questions. If you, let's say you have questions about your specific sites that you don't want, talked about in public, give me a call. We can sign NDAs. We are a product company. Okay, we don't sell services. Call us up. A bit of consulting about what's the best way forward is stuff that I love to do, and I love to learn about what your needs are. So by all means, reach out. Thank you.
Thank you all very much, and enjoy the rest of your day.
Stay safe.